Every boat sitting in the water is being slowly eaten alive by an electrical process most owners never notice happening and never see coming, as metal parts below the waterline quietly dissolve, atom by atom, into the surrounding water. A $9 sacrificial zinc, replaced on a simple schedule, is the only thing standing between that process and your propeller, your shaft, and your engine's underwater metal components. There's a reason this process picks certain metals to destroy first, completely bypassing others sitting right next to them in the same water, and it's not random. Understanding that one detail is what separates an owner who never has a corrosion problem from one who replaces an expensive propeller every couple of seasons without ever knowing why. The Independence Files runs on one rule: cheap, explainable, no upsell. Subscribe if you want the next one of these before you go looking for it yourself. Underwater metal components on a boat, propellers, shafts, trim tabs, and outdrives routinely cost hundreds to thousands of dollars to replace. When galvanic corrosion is left unmanaged, it doesn't just slightly shorten their lifespan, it can visibly pit, crumble, and structurally weaken metal that looked completely fine on the outside just a season earlier, sometimes catastrophically enough that a part fails entirely while the boat is in use. Saltwater environments make this timeline especially fast. The same water that makes boating possible is also an excellent electrical conductor, which is exactly what makes galvanic corrosion move quickly rather than taking years to become noticeable. A neglected saltwater boat can show serious pitting on unprotected metal within a single season, while the same neglect in freshwater typically takes considerably longer to produce comparable damage. What makes this especially frustrating for boat owners is how gradual and invisible the damage is day to day. Nobody watches their propeller corrode in real time. The boat runs fine, looks fine, and then during a haul-out or routine inspection, there's suddenly visible pitting, thinning, or a zinc anode that's completely dissolved away, with no single dramatic moment anyone could have caught in between. Here's what almost no boat owner learns until someone explains it directly. This isn't rust, and it isn't simple saltwater wear. It's an electrochemical process. When two different metals sit in the same electrically conductive water, one of them acts like the negative terminal of a battery and slowly gives up metal ions into the water, while the other is protected. Which metal loses that fight depends entirely on each metal's position on a well-documented electrochemical scale, not on which one happens to be more expensive or important to the boat. So here's the real question worth asking. If this process is going to happen regardless, because it's basic electrochemistry, not a defect, wouldn't it make more sense to control exactly which metal loses, rather than leaving it to chance which expensive component becomes the sacrifice? Think of it like a lightning rod on a building. A lightning rod doesn't stop lightning from striking nearby. It simply gives electricity an easier, preferred path to follow, protecting everything else around it by being the thing that takes the hit instead. A sacrificial zinc anode works on exactly that principle electrochemically. Zinc sits at a position on the electrochemical scale that makes it eager to corrode before more valuable metals like bronze, steel, or aluminum will. So as long as zinc is present and making good electrical contact, it takes the electrochemical hit instead of the propeller or shaft. Mechanically, this works through simple electron flow. In an electrically conductive medium like saltwater or even mineral-rich freshwater, a more active metal like zinc gives up electrons more readily than metals like bronze or stainless steel. Connect them electrically, which happens automatically anytime they're both submerged and part of the same boat's metal structure, and the zinc continuously loses metal ions into the water in place of the more valuable, more noble metals nearby, exactly as intended. This isn't a new or obscure protective technique. Sacrificial anode protection has been used on ships, pipelines, and underwater infrastructure for well over a century, and the same electrochemical principle protects buried steel pipelines, offshore oil platforms, and ship hulls, just at a much larger industrial scale than a single boat's propeller. Engineers didn't invent this specifically for recreational boats. They borrowed a well-established industrial corrosion control method and scaled it down. What's interesting is that this principle was documented and put to practical use long before anyone fully understood the underlying atomic chemistry behind it. Early observations that certain metal pairings protected one metal at the expense of another predate, a complete scientific explanation of exactly why, similar to how many practical engineering solutions arrive well ahead of the full theory, explaining them. Ships were being protected with sacrificial metal plates well before the electrochemical series was formally documented and understood the way it is today. Manufacturers of sacrificial zinc anodes published specifications for exactly which metal to use in which water type: zinc for saltwater, aluminum or magnesium anodes for freshwater or brackish conditions, since the same principle requires matching the sacrificial metal correctly to the water's conductivity and mineral content for it to work as intended. Boat owners and marine mechanics who track anode condition at each haul-out report a consistent, easily observable pattern. Boats with properly sized and maintained zinc anodes show minimal pitting or wear on their actual propellers and shafts, while boats with missing, undersized, or long-neglected anodes show measurably worse corrosion damage on those same expensive components, season after season. 3 separate threads pointing the same direction. Over a century of industrial sacrificial anode precedent across multiple applications, direct manufacturer guidance on matching anode metal to water type, and a consistent, visually confirmable pattern reported by boat owners and marine mechanics inspecting real boats. That's convergent evidence, not a single unverified claim. It's worth being precise about what varies here. Corrosion rate depends heavily on water salinity, water temperature, how much dissimilar metal is present on a given boat, and even electrical interference from nearby boats or dock wiring. There's no single universal timeline that applies identically to every boat in every location. What's consistent is the underlying mechanism and the fact that a properly functioning zinc anode measurably slows damage to everything else. So if this is such a well-understood, century-old protective principle, why do so many boat owners still end up with corroded propellers and shafts? It comes down to a simple, predictable gap. A zinc anode does its job silently and invisibly, dissolving away exactly as designed, with zero indication above the waterline that anything is happening at all. An owner has to actively remember to check it, usually only visible during a haul-out, rather than getting any kind of ongoing signal that it needs attention. There's a simpler reason underneath that, too. A completely dissolved zinc anode looks, to an untrained eye, like nothing at all. It's just gone, blending into the general appearance of underwater hardware. There's no dramatic failure moment pointing back to the missing anode as the cause, even though the resulting propeller damage traces directly back to it. As for what this actually involves, a standard sacrificial zinc anode, sized to match a given boat's shaft or hull mounting point, typically costs around $9 for a basic replacement unit. It bolts or clamps onto the same mounting point the original anode occupied, maintaining electrical contact with the boat's underwater metal so the protective circuit stays intact. The mechanism mirrors the lightning rod principle directly. As long as the zinc anode remains electrically connected and has enough remaining material to keep sacrificing itself, it continues absorbing the corrosive electrochemical process instead of the boat's more valuable metal components. Once an anode has visibly worn down to a small fraction of its original size, it's approaching the point where it can no longer offer full protection, and replacement restores that protection immediately. Now, back to the detail I mentioned at the start. Why this process targets specific metals and not others. Every metal has a position on what's called the galvanic series, ranking how readily it gives up electrons compared to other metals. Zinc sits well above bronze, stainless steel, and most other boat hardware on that scale, which is exactly why it reliably corrodes first when the two are electrically connected. It's not random chance, it's a predictable, documented electrochemical hierarchy that anode selection is built entirely around. There are honest limitations worth being upfront about here. Using the wrong type of anode for your water conditions, aluminum or magnesium anodes in saltwater or zinc anodes in freshwater, can result in inadequate protection or, in some cases, accelerated corrosion of the anode itself without properly protecting other metals. Matching anode type to water type isn't optional. It's the core requirement that makes this whole system function correctly. Paint and coatings on underwater metal can also interfere with anode effectiveness if applied incorrectly. An anode accidentally painted over loses electrical contact with the surrounding water and stops providing any protection at all, even though it may still look physically intact during a quick visual check. Electrical issues aboard the boat or stray current from a marina's dock wiring can also overwhelm normal sacrificial protection entirely, a phenomenon called stray current corrosion, which behaves differently and can cause rapid damage even with properly maintained anodes in place. This fix addresses ordinary galvanic corrosion, not electrical faults introducing outside current into the water. Anode placement and quantity matter too, particularly on larger boats with multiple underwater metal components spread across different areas of the hull. A single anode protects components in its immediate electrical vicinity, not the entire underwater structure of a large vessel, and boats with metal spread across a wider area often need multiple anodes positioned near each cluster of components to maintain full protection. This isn't a substitute for regular haul-out inspection of underwater metal components, and it's not being presented as one. It manages exactly one process: galvanic corrosion between dissimilar metals, nothing more and nothing less. Which loops back to where this started. The same sacrificial anode principle applies just as directly to a boat trailer's submerged metal parts during frequent launches, using the identical electrochemical logic just applied to a different set of components. Every boat sitting in the water is part of a slow electrochemical process, whether anyone's paying attention or not. The only real choice is which metal takes the damage. If you've checked your own anodes recently, or you're not sure which type your boat and water conditions actually call for, drop it in the comments below. I read all of them, and I'll do my best to help you figure it out.